All right. So let's finish up with our discussion of trig. Actually, we're going to be talking about trig throughout the semester. It's going to continue to be an important tool for us, but this is our last section specifically about trig, and it's about solving trig equations. So in 3.8, we talked about trig identities, which are statements that are true regardless of the value that you plug in for the variable. Trig equations are statements that are only true for certain values of the variable, and we would like to solve for those values. So that's what we're going to talk about in this section. Now here's how this works, or at least here's my approach to solving trig equations. You may have a different approach that you like better, and that's fine. More power to you. But just hear me out here and maybe give my approach a try, because I think it might help some of you who are kind of confused on this topic. It's been my experience that solving trig equations is a topic that gives students a lot of trouble. So hear me out on this, and maybe try to use this approach that I'm giving you here. So let's say that alpha is a solution to the equation sine x equals k. In other words, if we plug in alpha, we get sine alpha equals k, right? If that's the case, then alpha plus 2 pi, alpha plus 4 pi, and in general, alpha plus 2n pi are all also going to be solutions, because sine is a periodic function with period 2 pi. But there are other solutions to this equation as well. Okay? For the sine function, if alpha is a solution, then so is pi minus alpha. And here's why. Here's a visual understanding of why this is the case. So let's say that you have this equation sine x equals k, and you're trying to find all of the angles that make this statement true. And let's say that one of the angles that makes the statement true is the angle alpha. Now, what does that mean? That means that sine of this angle, which, by the way, corresponds to the y value here, is k. If that's the case, then there is another solution up here, right? This solution, or this angle, would also give us k when we take sine of that angle, right? So there's one solution, there's another one, right? This thing we could maybe call beta or something, right? So alpha and beta are both solutions to this equation, sine x equals k. Now, how do you describe beta? Well, it turns out that beta is going to have the same reference angle. So the reference angle here is going to be alpha, which means that beta is just 180 degrees minus alpha. Or, in other words, it's pi radians minus alpha. So beta is pi minus alpha. Okay? So, if alpha is a solution, then so is pi minus alpha. That's true when you're working with sine. When you're working with cosine or tangent, it's a little bit different, right? So for the sine function, if sine x equals k, then x equals sine inverse of k plus 2n pi is one set of solutions, and then the other set of solutions is pi minus sine inverse of k plus 2n pi, right? So those are the two types of solutions. They're going to generate two different infinite solution sets, right? So you're going to have infinitely many solutions to this equation. Okay, so that's for the sine function. Now for the cosine function, it's a little different. For the cosine function, let me draw a picture of that. So for the cosine function, if you have some statement that says cosine x equals k, and you know that alpha is a solution, well, if alpha is a solution, now cosine corresponds to x values, right? So if you're saying cosine x equals k, or sorry, then if you're saying cosine alpha equals k, then you're going to have another solution down here, right? Whose reference angle is also alpha, but the angle itself would actually be 360 degrees So it would be 360 degrees minus alpha. Or in other words, it would be 2 pi minus alpha. So for the cosine function, the two solution sets that you get are cosine inverse k and 2 pi minus cosine inverse k. And then, of course, every integer multiple of 2 pi is also going to be a solution. Okay. For tangent, it's a little bit different. Tangent has a period of just pi, right? Not 2 pi. And so you don't get two different solutions, I guess. You just get one solution, but it repeats every pi units instead of repeating every 2 pi units, right? And that's how the tangent function works. Okay, so how do we solve a trig equation? Well, we try to manipulate the equation so that it looks like one of these three forms. And once it's in one of those three forms, then we apply the appropriate rule. So let me give you several examples of this. So here we have sine 2x equals 1/2. This is already set up for us, right? This is already in this top format right here, sine x equals k. All right, so it's already in this top format here, sine x equals k. So right away we can say, well, if sine x equals k, then x is sine inverse of k. In this case, our argument is 2x. So we're going to say, all right, so then 2x equals sine inverse of 1/2, right, plus 2n pi, or 2x equals pi minus sine inverse of 1/2 plus 2n pi. Right? Those are the two possible solutions. And actually, they're not just two solutions, they're two sets of solutions. Now, we haven't solved for x, though, you may have noticed, right? We still have to divide through by 2 to finish solving for x. Before I do that, maybe let's figure out what sine inverse of 1/2 is. So we're looking for an acute angle such that sine of that angle is equal to 1/2. I think that 30 degrees does the trick. Or since we're looking for the solutions that live in the interval 0 to 2 pi, it seems like we're working with radians. So in radians, this would be pi over 6, right? So sine inverse of 1/2 is pi over 6. So we know that 2x is pi over 6 plus 2n pi, or 2x is pi minus pi over 6. That would be 5 pi over 6 plus 2n pi. Now we finish solving for x by dividing through by 2. So we divide through by 2, we get x equals pi over 12 plus n pi. Make sure that when you divide through by 2, you divide each term by 2, right? So we're dividing each and every term by 2, and here the 2's cancel and leave us with n pi. That's very important, okay? Same thing over here, we're going to get x equals 5 pi over 12 plus n pi. Those two solutions will generate all of the solutions to the original equation. So our solution set, so all of our solutions are going to be these things, pi over 12 plus n pi, and 5 pi over 12 plus n pi, where n is an integer. Right, so those are all of the solutions. Now, if we're only interested in the solutions that live in the interval from 0 to 2 pi, then we would intersect this set with this interval. In other words, we can take turns plugging in numbers for n into these two rules, and then we're going to write down only the ones that are between 0 and 2 pi. So focusing on the pi over 12 for a second, if I plug in a -1, I'm going to get pi over 12 minus pi. That's going to be something less than 0. So plugging in -1 isn't going to generate a solution that lives inside of this interval. If I plug in 0, then I get pi over 12. That's in the interval for sure. If I plug in 1, then I get pi plus pi over 12. That's also in the interval, right? So pi plus pi over 12 would be 13 pi over 12. So that's in the interval for sure. If I plug in 2 for n, I'm going to get 2 pi plus pi over 12. That's obviously going to be bigger than 2 pi, so it's not going to be in the interval. So I'm not going to write down that solution. That does it for pi over 12. Now let's look at 5 pi over 12. Again, if I plug in something like -1, I'm going to get 5 pi over 12 minus pi. Pi is like 12 pi over 12, right? So 5 pi over 12 minus 12 pi over 12 is obviously going to be less than 0. So if I plug in -1, the result is not in this intersection. If I plug in 0, I get 5 pi over 12. That's definitely in there. If I plug in 1, I get 5 pi over 12 plus pi, right? Pi, again, is 12 pi over 12, so that would be 17 pi over 12. That's still in the interval, right? 2 pi is like 24 pi over 12, so 17 pi over 12 is still in there. If I plug in 2, then I get 2 pi plus 5 pi over 12. That's obviously bigger than 2 pi. So that does it, right? Those are all of the solutions that live in the interval from 0 to 2 pi. Okay, so these are all of the solutions, and then these are the ones specifically that are between 0 and 2 pi. Of course, you could do the same thing with degrees. You could convert all of this into degrees, and it would still work. Okay. So that's part A, sine 2x equals 1/2. Let's look at the next one. Sine x over 2 equals -√3 over 2. Okay, similar deal, right? Here we would say, okay, if sine x over 2 is -√3 over 2, then it must be the case that x over 2 is equal to sine inverse of -√3 over 2 plus 2n pi, of course, or that x over 2 is equal to pi minus sine inverse of -√3 over 2 plus 2n pi. Okay, so let's think about what sine inverse of -√3 over 2 should be. So sine of √3 over 2, or sine inverse of positive √3 over 2, maybe I should say. I think that would be pi over 3. So sine inverse of -√3 over 2 is going to be negative pi over 3. Okay, so we're going to get x over 2 equals negative pi over 3 plus 2n pi, or x over 2 equals pi minus negative pi over 3, we decided, right? Pi minus negative pi over 3, that's pi plus pi over 3. That's 3 pi over 3 plus pi over 3, so 4 pi over 3 plus 2n pi. Now we haven't finished solving for x, right? We need to multiply through by 2. So multiplying through by 2, we get x equals negative 2 pi over 3 plus 4n pi, or x equals 8 pi over 3 plus 4n pi. And those are all of the solutions, right? So all of our solutions are going to be generated by those two rules, negative 2 pi over 3 plus 4n pi, or 8 pi over 3 plus 4n pi, where n is an integer. Now, what about the solutions that live in the interval from 0 to 2 pi? So now we're going to take the intersection of this set with this set, okay? If I plug in a negative number, obviously I'm going to get a negative number. So that's no good because I'm only interested in the numbers between 0 and 2 pi. If I plug in 0, I still get a negative number, so that's no good. If I plug in 1, then I get negative 2 pi over 3 plus 4 pi. So negative 2 pi over 3 plus 4 pi. That's equal to 10 pi over 3. Well, 2 pi is 6 pi over 3, right? So 10 pi over 3 is way more than 2 pi. So when I plug in 0, the number's too small. When I plug in 1, the number's too big. So none of these numbers are going to be inside of this interval. So nothing generated by this rule is going to be inside of this interval. What about 8 pi over 3 plus 4n pi? If I plug in, say, negative 1, I get 8 pi over 3 8 pi over 3 minus 4 pi. That's a negative 4 pi over 3. So when I plug in negative 1, that's not in there. If I plug in 0, then I just get 8 pi over 3. But 2 pi is the same thing as 6 pi over 3. So 8 pi over 3 is too big. So when I plug in negative 1, the number's too small. When I plug in 0, the number's too big. So nothing generated by this rule is going to end up inside of this interval. That exhausts my options, right? So in the interval from 0 to 2 pi, there are no solutions to this problem. It's not that there aren't solutions to the equation. There are, right? There are infinitely many solutions to the equation, right? It's just that none of them are between 0 and 2 pi. Okay, so that's what we're saying. All right, so that's how that one works. Let's look at the next one. Cosine x equals 1. Okay, cosine x equals 1. So this would mean that x equals cosine inverse of 1 plus 2n pi, or x equals 2 pi minus cosine inverse of 1 plus 2n pi. Notice, since this is the cosine function, the second solution is 2 pi minus the first one. With the sine function, the second solution is pi minus the first one. But with cosine, it's 2 pi minus the first one. So just be aware of that, right? We talked about why that is on the previous page, right? Here, beta is just pi minus alpha. Here, you know, if we call this thing beta, beta would be 2 pi minus alpha, right? So it's a different rule. The good news is that x is already solved for here. There's really no additional work to be done other than to simplify these things. Cosine inverse of 1. Cosine of 0 radians or 0 degrees is equal to 1. So this is going to be 0 plus 2n pi. This one is going to be 2 pi minus 0. So in other words, just 2 pi plus 2n pi. Now, let me take this one step further, right? So this is going to be 2n pi. This one would be, well, I guess you could say 2n plus 1 times pi. Or how would we say it? 2n plus 1 times pi? It doesn't really matter. Yeah, what I'm thinking is, you know, you could factor out the 2 pi, and you'd be left with n plus 1. So you'd have 2 times n plus 1 times pi. But it doesn't really matter. What I want to point out is that these two sets are the same. They generate the same set of numbers, right? Like if you start to list off, the elements of this set, right? If you plug in like negative 2, you're going to get negative 4 pi. If you plug in negative 1, you get negative 2 pi. If you plug in 0, you get 0. If you plug in 1, you get 2 pi. If you plug in 2, you get 4 pi, and so forth. If you think about this set, or the set that this rule generates, it's going to be the same thing, right? If you plug in negative 2, negative 2 plus 1 is negative 1. Negative 1 times 2 is negative 2. You get negative 2 pi. If you plug in negative 1, you get 0. If you plug in 0, you get 2 pi. If you plug in 1, you get 4 pi. If you plug in 2, you get 6 pi, and so forth. But these are exactly the same set, right? They're exactly the same set because they both extend forever in the negative and positive directions. So they're going to contain exactly the same numbers, okay? So in reality, when we write down our solution set, right, all of our solutions, they're all going to have the form 2n pi, where n is an integer. Okay, this rule is really, it generates the same set as this rule, right? So this is our solution set. These are all of our solutions. Now, if I'm interested in the solutions that live in the interval from 0 to 2 pi, If I plug in something negative, I'm going to get something negative, right? That's no good. If I plug in 0, I get 0. That's in the set. If I plug in 1, I get 2 pi, but 2 pi is not in the set, right? We're using a parenthesis here. So I think 0 actually is the only solution that actually lives between 0 and 2 pi. Right? That's the only solution to the equation. Okay? So that's how you would solve that one. By the way, you don't have to do this little step right here. I was just writing this out to show you why these two rules are actually going to generate the same set, right? Very good. Let's do a tangent. Tangent x equals -2. Okay, so for the tangent function, the rule is a little bit different, right? So whenever you have tan x equals k, then you just get one solution, right? It's tangent inverse of k. But it repeats every pi units instead of repeating every 2 pi units, okay? So it's tangent inverse of k plus n pi. All right? So in this case, x is tangent inverse of -2 plus n pi. And that's all there is to it. I don't know tangent inverse of -2 off the top of my head, so I'm going to use my calculator, make sure I'm in radian mode. So tangent inverse of -2 is about -1.11. So here's what I would say. I would say x is approximately -1.11 plus n pi. This is really the exact solution, right? There's no way to make it cleaner than that. This is the approximate solution. So if I wanted to express all of my solutions, well, the exact forms would be tangent inverse of -2 plus n pi, where n is an integer. Okay, but this is approximately equal to -1.11 plus n pi, where n is an integer. So if I wanted to describe the solutions that live in the interval from 0 to 2 pi, well, then I could start to plug in numbers for n. Now, clearly, if I plug in a negative number, I'm going to get a negative answer. That's no good. Even if I plug in 0, I end up with something negative, so that's not any good either. But if I plug in 1, I would have tangent inverse of -2 plus pi. And that's about 2.03, so that's definitely in the interval. So if I'm giving the exact answer, it would be tangent inverse of -2 plus pi. Okay, so that's one solution. If I plug in 2, I'm going to get 2 pi minus something, so that's also definitely going to be a solution. Tangent inverse of -2 plus 2 pi. But if I plug in 3, then I think I think that goes too far, right? Tangent inverse of -2 plus 3 pi is approximately 8.317, whereas 2 pi is approximately 6.28. So if I plug in 3, the number is too big, right? These are the only two solutions. Now, if I want to give decimal approximations, I can do that. Right? Tangent inverse of -2 plus pi is about 2.03. And tangent inverse of -2 plus 2 pi is about 5.18. 5.18. Okay. So there you go. Okay, so we've seen all three cases when you have sine, cosine, tangent. You can always turn a trig equation into one of those three, right? So if you end up with like cosecant x equals whatever, just change it to sine. Change it to 1 over, change it to sine x equals 1 over whatever. Okay. But so since we've seen some examples of each of these now, let's look at some more interesting examples, like part E. Okay. So here we've got 3 secant x minus pi over 6, and here we've got a secant x minus pi over 6. Notice that they're really the same variable. So we have 3 copies of this thing on the left-hand side and 1 copy of it on the right-hand side. So we can just move this copy over there, and that would give us 2 secant x minus pi over 6 minus 1 equals 3. Then we can add 1 over to the other side. 2 secant x minus pi over 6 equals 4. And then we could divide by 2. Secant x minus pi over 6 equals 2. Now it's looking much better, right? Now it's looking like the format we like. Trig function of something equals some number, right? That's the format that we're going for. I can change this one into cosine, right? I can say cosine x minus pi over 6 equals 1/2, right? Reciprocal identity. Okay, so now what this tells us is that x minus pi over 6 equals cosine inverse of 1/2 plus 2n pi, or x minus pi over 6 equals 2 pi minus cosine inverse of 1/2 plus 2n pi. All right, those are the 2 possible solutions. Cosine inverse of 1/2, I think, would be pi over 3, right? Two pi is 6 pi over 3. Right? 6 pi over 3 minus pi over 3 is going to be 5 pi over 3. And now to finish solving, we add pi over 6 to both sides, right? Pi over 3 is 2 pi over 6. So you add pi over 6, you get 3 pi over 6. 3 pi over 6 reduces to pi over 2. Uh, 5 pi over 3 would be 10 pi over 6. So plus another pi over 6 would be 11 pi over 6. Okay, so there are the 2 rules that will generate all of the solutions. I'm running out of space down here, so I'm going to write my answer up here instead. So all of the solutions are going to be pi over 2 plus 2n pi and 11 pi over 6 plus 2n pi, where n is an integer. Whoops. Okay. The ones that live in the interval from 0 to 2 pi, though, well, let's see. Can't plug in -1. If I plug in 0, I get pi over 2. If I plug in 1, I get something bigger than 2 pi. Over here, if I plug in -1, 2 pi is 12 pi over 6. 11 pi over 6 minus 12 pi over 6 is going to be negative pi over 6, so it's not in the interval. If I plug in 0, I get 11 pi over 6. If I plug in 1, I get something bigger than 2 pi. So those are the 2 solutions that live in the interval from 0 to 2 pi. Okay, so that's how we would do part E. How many more of these do we have? I think I've got 3 more examples, okay? 3 more examples. So I've got one, sine 2x minus 1 times root 3 tangent x plus 1 equals 0. And I'm saying note to self, check solutions on this one. Okay, yeah, I suspect. So remember that the tangent function has some domain issues. There are places where the tangent function is undefined. So if we solve this thing and we get something like x equals pi over 2 as a possible answer, well, it can't be an answer because tangent of pi over 2 is undefined. There's an asymptote there, right? Okay, well, how do we solve this one? Well, fortunately, this one has already been factored, and so what we can do is apply the zero product principle, right? We know if sine 2x minus 1 times root 3 tangent x plus 1 equals 0, then it should be the case that either sine 2x minus 1 is 0, or root 3 tangent x plus 1 is 0. So we'll look at those two cases. And by the way, it's like this, right? 2x minus 1. Or, and leave yourself plenty of space, because I think we're going to have multiple rules here that are going to generate multiple sets of solutions. But let's see what we get now. So here I can add one, say sine 2x equals 1. And then I can say, all right, if sine 2x equals 1, then it should be the case that 2x is sine inverse of 1, or that 2x is equal to pi minus sine inverse of 1. Okay, those all come from this first equation. Now the second one we can subtract 1 and then divide by root 3. We're going to get tangent x equals negative 1 over root 3. Or if you like to rationalize, that would be negative root 3 over 3, right? That tells us that x is tangent inverse of negative root 3 over 3 plus n pi. And remember, tangent, you only have one rule, one generating rule. So these are our three generating rules, right? These three right here. And I guess we're not quite done here because we need to divide through by 2, right? Also, we should probably figure out what sine inverse is and what tangent inverse is. So let's do all of that, right? Sine inverse of 1, that's going to be pi over 2, right? So we get pi over 2 plus 2n pi, or 2x is pi minus pi over 2. Well, wouldn't you know it? That's just pi over 2 plus 2n pi. So this is redundant, right? This gives us the same solution set. And then from here, tangent inverse of negative root 3 over 3. So we would be looking for where sine is equal to root 3 over 2. That happens when that happens at pi over 3. So tangent inverse of negative root 3 over 3 would be negative pi over 3. So x is going to be negative pi over 3 plus n pi. By the way, if you don't like doing that in your head, you can use a calculator. Just use your calculator. It's fine. Make sure it's in radian mode, though. And make sure that it's going to give you the exact answers in terms of pi, not some decimal approximation. Okay, so now, one last thing, I've got to divide by 2 here. X is pi over 4 plus n pi, or x is negative pi over 3 plus n pi. Right, there are our solutions. Now, here's where the checking the solutions bit is important, because I think that actually this rule is not going to generate any valid solutions, because, as we said, that's not true. No, that's fine. That's fine, actually. Pi over 4 is fine. I was thinking pi over 2. Right, we would have an issue if x was pi over 2, but pi over 4 is okay. Okay, so then I think we're okay, actually, right? I think that pi over 4 and negative pi over 3, they're both fine. We don't have any domain issues with the tangent function with either of those values, so I think we're okay. So all of our solutions then are going to be pi over 4 plus n pi and negative pi over 3 plus n pi, where n is an integer. So then the solutions that live in the interval from 0 to 2 pi, obviously if I plug in negative 1, that's going to be less than 0. If I plug in 0, I get pi over 4. If I plug in 1, I get 4 pi over 4 plus pi over 4 is 5 pi over 4. If I plug in 2, I've gone too far, right? Moving on to the next one. If I plug in -1, that's going to be negative. If I plug in 0, it's going to be negative. If I plug in 1, I'm going to get pi minus pi over 3 is 2 pi over 3. If I plug in 2, I have 2 pi minus pi over 3. 2 pi is 6 pi over 3. 6 pi over 3 minus pi over 3 is 5 pi over 3. And then if I plug in 3, I think I will have gone too far. So, so there we go. And yeah, we can check each of these, but they're not going to be problems in the tangent function. So I think we're good there. So that's how we would take care of a situation like this. Looking at part G, then I think that we have a little bit of a clue here. Notice that this is really kind of the form 2x squared minus x minus 1. But x is cosine theta, right? That's really what we have going on. Well, how would we solve this? We would factor, right? And if we can't factor, then we would use Pythagorean, or not Pythagorean. If we can't factor, we would use the quadratic formula. But let's see if we can factor this. If it factors, it should look something like 2 cosine theta, and then cosine theta, so that we can get a 2 cosine squared theta in the first position there. And then to get a 1, we must have a 1 and a 1. And then because it's a negative, we know that one sign must be positive and the other one must be negative. Now, we need to get a negative cosine theta. So I'm thinking this one needs to be negative so that we get negative 2 cosine theta. And this one needs to be positive so that we get a positive cosine theta. So that together, the outside and the inside will give us a negative 1 cosine theta. So this factorization does the trick. Now that we've factored it, we can say, oh, I'm going to have to write small. We can say 2 cosine theta plus 1 equals 0, or cosine theta minus 1 equals 0. Here we're going to get cosine theta equals negative 1/2, and here we're going to get cosine theta equals 1. And now this is where I need to start writing small. So if cosine theta equals negative 1/2, then that means that theta equals cosine inverse of negative 1/2 plus 2n pi, or theta equals 2 pi minus cosine inverse of negative 1/2 plus 2n pi. That just, those two solutions come from this first case. And then we're going to have two more solutions that come from the second case, right? So if cosine theta equals 1, then that would mean that theta equals cosine inverse of 1 plus 2n pi, or that theta equals 2 pi minus cosine inverse of 1 plus 2n pi. So 4 possible generating rules here. Let's simplify them. Cosine inverse of negative 1/2. Of course, you can just plug that into your calculator, but let me see if I can work it out in my head. Cosine inverse of negative 1/2. So cosine inverse of positive 1/2 would be pi over 3. So cosine inverse of negative 1/2 would be 2 pi over 3. Okay, so theta is 2 pi over 3 plus 2n pi, or theta equals 2 pi minus 2 pi over 3. 2 pi is 6 pi over 3. 6 pi over 3 minus 2 pi over 3 is 4 pi over 3 plus 2n pi. Or theta equals, cosine inverse of 1 would be 0, right? So 0 plus 2n pi. Oh, we've already seen a situation kind of like this, right? Theta equals 2 pi minus 0 plus 2n pi. So remember, we saw this kind of on the previous page. These two things generate the same solution set. So really, these two things are the same thing as just saying 2n pi. So really, we just have 3 generating rules for our solution set. So we can say all of our solutions are going to be of the form 2 pi over 3 plus 2n pi, 4 pi over 3 plus 2n pi, or just straight up 2n pi, where n is an integer. Okay, those are all of the solutions. Now, if we want the solutions that live in the interval from 0 to 2 pi, let's see. I'm going to start with 2n pi. If I plug in a -1, too small. If I plug in 0, I get 0. If I plug in 1, it's 2 pi, that's too big. All right, so that does it for 2n pi. Now, the other two. If I plug in something negative, it's going to be too small. If I plug in 0, I'm going to get 2 pi over 3. That's definitely in there. If I plug in 1, it's going to be too big. And then moving on to the 4 pi over 3. If I plug in a negative, it's going to be too small. If I plug in 0, I get 4 pi over 3. And if I plug in 1, it's too big. So I only get 3 solutions that fall in the interval from 0 to 2 pi. But there you go. That's how that one works. And I apologize that I've just been talking and talking. I'm feeling exhausted, to be honest with you. But I have one more, one more example to show you. This one is interesting because we have a cosine. We have a cosine in there, but we also have a sine in there. So what we're going to have to try to do is either rewrite the sine as a cosine or rewrite the cosine as a sine. Now, we don't have anything really that tells us what sine to the first power is equal to in terms of cosine, but we do have a Pythagorean identity that tells us what cosine squared is equal to in terms of sine squared, right? We know that since cosine squared plus sine squared equals 1, that cosine squared should just be 1 minus sine squared. So I can replace the cosine squared here with a 1 minus sine squared, and then that way this equation is going to be rewritten all in terms of sine only, right? So let's do that, right? I have 2 times 1 minus sine squared theta plus 3 sine theta minus 3 equals 0. So that's 2 minus 2 sine squared theta plus 3 sine theta minus 3 equals 0. 2 minus 3 is -1, so I'm going to have -2 sine squared theta plus 3 sine theta minus 1 equals 0. And then I'm also going to just multiply through by a -1 so that my leading coefficient is positive. It's just easier for me to factor this way. I wonder if this one does factor. We can try. Whoops. Let me try again. 2 sine theta. It's got to be a 1 and a 1. And they have to be negative. They both have to be negative in order for us to get a positive here and a negative there. Does that give us what we want? Oh, I think so, right? -2 sine theta minus sine theta is a -3 sine theta. So there we go. So now we're going to get 2 sine theta minus 1 equals 0, or sine theta minus 1 equals 0. So sine theta is 1/2, or sine theta equals 1. The rest is history, right? You've seen this so many times at this point. I'm just going to stop talking and I'm just going to write, okay? I'm running out of room. Okay, Sine inverse 1/2 should be pi over 6. Sine inverse of 1 is pi over 2. And pi minus pi over 2 is again pi over 2, so this one is redundant. Okay. And that will do it. That does it. Okay. Whew. What a section of material. But that does it, and that does it for our discussion of trig, at least for now.